We now invite Mr. M. Balamurugan, Council Member of the IIF Chennai Chapter, to introduce our next speaker, Mr. S. Kannan, Deputy Manager, Metallurgical Quality Control, and Mr. S. Balamurugan, Senior Engineer, Metallurgical Quality from Brakes India Private Limited, Foundry Division.
I'm very happy to introduce the next speaker from Brakes India Unit 2, Mr. S. Kannan. He is a Deputy Manager, Metallurgical Quality. He has 18 years experience. And Mr. Balamurugan, S. Balamurugan, is a Senior Engineer, Metallurgical Quality. He has 8 years experience. So we are waiting for your presentations, please.
Good afternoon, everyone. We would like to thank everyone for the opportunity to share our experience in Brakes India Foundry Division. Here we are going to brief about the improvement done in the shop floor on quality improvement on thermal analysis of metal. So before going into the topic, I want to brief about our Brakes India Foundry Division and our brakes units. So Brakes India having 4 business units: light vehicle brakes, heavy vehicle brake units, iron castings. Iron castings is the Brakes India Private Limited Foundry Division, and friction and aftermarket division. So our topic is thermal analysis. It belongs to our Brakes India Foundry Division unit. So we are having four strategic locations in our Foundry Division: Solinger, Naidupeta, Jagadia, and Oman. So this is our legacy of Brakes India Foundry Division. We have started our journey in 1981. Brakes India Foundry is the largest manufacturer and exporter of automotive castings, and having a capacity of 2.22 lakhs of iron castings annually. Our company is also focusing on green manufacturing and sustainable recyclability on sustainability. So our product portfolios: brake parts, steering knuckles, chassis parts, engine parts, and charger parts. So what makes us one of the top foundries in the world are strategic investments in technology and process innovation. This is the area our topics are going to discuss about. And we are market leader in precision and ability to produce complex parts that are high on measurability, setting objectives to eliminate, control, and minimize carbon footprint. Pioneers of the world first green iron casting business in one of our unit, and global presence and local support. Highly skilled individuals having product knowledge and the speed of new product development. Increasing total renewable energy share from 20% to 93% by 2026, which is we are almost achieved in the current year. Commitment to sustainable resource use and protection of ecosystem. So our topics discuss on the strategic investment in technology and process innovation, which includes simulation software, a fully fledged in-house pattern and die shop with CAD, CAM and CAE facilities, melt quality control, and advanced non-destructive testing techniques. Our topics comes under the melt quality control, which is nothing but thermal analysis system. So my colleague will explain further slides.
Good afternoon, everyone. We listed some of the major factors influencing the metallurgical quality. Some of them chemical composition like carbon, silicon, and other alloying elements. Charge materials, foundry returns and borings, and then began. Charging sequence, and then magnesium treatment practice, and pouring temperature and inoculation practice, and the thermal properties of an alloy, and then gating methods, and then shakeout time. So those are the key major factors which are affecting the metallurgical qualities, like microstructure and mechanical properties and sinkage of the castings. So these properties are vary from the melt to one melt to another melt on every day. So why chemistry is not enough? Optical emission spectrometers is given only the information on what are the elements present in the liquid metal, but did not give the information on compounds and nucleation properties of the liquid metal, and then it does not give the information on graphite precipitation. So when you getting a good quality of melt, you have to understand the solidification behavior of the liquid metal in the mold. So it can be achieved through thermal parameters. Next. So it can be achieved through the thermal parameters. Thermal analysis is based on monitoring the solidification of a standardized test piece. It gives the time temperature curve. It is influenced by the metallurgical conditions in the mold. This enables to identification of liquid temperature and eutectic temperature from the solidification curve. So this from the information in thermal analysis makes it possible to fine tune every step in process to minimize the variation and optimize the properties.
So this thermal analysis, we can also use this time temperature print to the simulation software also by injecting this time temperature curve into the simulation software. So we can proactively eliminate the shrinkage, and we can assure more precise simulation by injecting this real-time time temperature curve into the simulation software. In addition to the chemical composition and other parameters, this is very useful when injecting this time temperature curve in the simulation software. So some key parameters of the thermal analysis are liquidus temperature. It's a first thermal arrest before the liquid is transformed into the solid, and next is eutectic low temperature, which is nothing but the start of nucleation, where the temperature starts increasing instead of decreasing, and the maximum temperature of the increasing period is nothing but eutectic high, and the recoalescence is nothing but the difference between the eutectic high and the eutectic low, which denotes the nucleation of the metal print. And last is solidus temperature, the point that can be found at the last part of the first derivative curve. So in between there are two precipitation is happening. The graphite factor 1 and the graphite factor 2. The graphite factor 1 is happening at the liquid semi-liquid stage. That is liquid to when the metal transforms from liquid to solid or semi-solid, the graphite precipitation will be happening. So higher the graphite precipitation at the liquids to solid, semi-solid transformation indicates the very good eutectic metal. And graphite factor 2 is nothing but the heat conductivity at the solid state. So lesser the value of graphite factor will give the good sign and higher amount of graphite present in the metal. So S1, S2, S3, these three surface phases are the difference between the this temperature liquidus and eutectic low and eutectic high, and the eutectic high in the solidus temperatures. So other key parameters in addition to these thermal analysis are carbon at liquidus temperature and the active carbon equivalent. Active carbon equivalent is we can find only this active carbon in the thermal analysis system only, not through the spectrometer. So even when we achieve carbon equivalent at 4.4 or 4.5 in the by calculating in the optical spectrometer, but it will show different in the thermal analysis system at 4.3 or 4.25, which is nothing but that is the actual active carbon equivalent than the shown in the spectrometer. So it is very important parameter to know the precipitation of graphite in the ductile.
thermal analysis is a metallurgical parameter. It gives the information on macro sinkages and micro sinkages and porosity and then inverse chill information. This defect can be controlled through thermal analysis parameters like TL, liquidous temperatures, and then TE low eutectic temperature, and then S1, surface representing primary austenite, and then graphite factors, and then recalcitrance. Those are the key parameters for controlling those defects. Some metallurgy related points, problems can be achieved through the above, I said the above parameters.
So in one of our line in Bricks India unit, we implemented all those thermal analysis parameters stage by stage, and we have achieved sinkage defect detections in one of our line. So how we can achieve, we can describe here. We decided to incorporate all the thermal analysis curves in the base metal as well as in the final metal. By continuously collecting all the data over the year, and we analyzed based on the good, bad, and the actual castings defects. We defined the specifications, all the parameters like carbon equivalent, carbonate TL as well as the TL, TE low, everything. Predicted the carbide and sinkage tendency with respect to thermal points, and continued implementing control limits for each critical parameter to eliminate sinkage tendency for each part numbers. So we can predict this. We can predict micro sinkage, carbides, as well as the mechanical properties through thermal analysis system. So this is one of the example of how we can control the mechanical properties also in the thermal analysis system. And this topic mainly focused on the sinkage, especially macro and micro sinkage. So this is one pictorial representation of the micro sinkage as well as the surface sinkage or macro sinkage. Micro sinkage presents at the inner portion of the castings in a spongy like structure, and surface and macro sinkage is present in the surface as well as inside the casting in a big very low conditions. So this is the achievements after implementing these parameters. Could you explain?
From the thermal analysis, we given the control for CTL, carbonate liquid temperature. First, we given the CTL control. After implementing this CTL control, we have drastically reduced the scrap due to sinkage. Before that, it was on a 0.43%, now achieved 0.30%. Drastically, approximately 30% rejection has been reduced. These controls are provided based on the data captured from the soft floor analysis more than a year, and checked the effectiveness of these parameters for few months. Then only we taken the control into this system. Apart from CTL, we decided some of the additional controls along with the CTL. We given some thermal parameters like TL and liquidous temperature, TE low, and then graphite factor, and then recalcitrance. After putting these controls along with the CTL, we drastically reduced the rejection from stage by stage, each and every stage. Finally, we achieved putting this TL control and then TE low control and GRFN and R control. We reduced the rejection level up to the 0.07%. Before that, it was on 0.43%. So we achieved almost 80% of the rejection. We eliminate through sinkage defect. After putting this thermal process parameter control, and some of the parts we eliminate the sinkages after putting this thermal process parameter control.
So, through melt quality being monitored and controlled using thermal analysis, apart from conventional spectrometer, prediction of metal quality before pouring into the metal, it is more quality assurance technique than the quality control. Reduction in scrap due to metal defects such as shrinkage, improvement in shrinkage defect in the castings, improvement in metallurgical quality. This requires lot of experiments and a lot of data collection is needed before implementing this thermal analysis system. So, thermal analysis allows the foundry to improve and control the metallurgical quality of the base and the final in daily production, optimize various processes in melting and treatment of iron alloys. Also, we can perform a quality control of incoming raw materials such as ferroalloys, ferrosilicon, ferrosilicon, magnesium, etc. before it comes to usage. It can be used for simulation software also. This is an advanced tool for research and development of materials. Thank you.
Thank you for sharing your company's experience in solving certain problems. Now I call upon Mr. K.S. Anbuselvan, National Council Member, IIF, to felicitate Mr. S. Kannan and Mr. S. Balamurugan with a traditional Angavastram and a memento.